Okay, I'm going to go ahead and get started. I don't know if other people are going to join us. I hope that they do. What I wanted to do is go over some things in a little bit more detail that I know many students find confusing. So I'm going to talk a little bit about the stuff in chapter 1, a little bit about the stuff in chapter 2. And then if you guys have questions about material that might be on the test, I want to make sure you have an opportunity to ask those as well. So I'm going to start by sharing my screen. All right, so in chapter 1, they talk about atomic structure. And they really just kind of dive into the modern view, which is fine. Sometimes in the past, I've gone through and discussed kind of the historical ideas that have been developed. So in the early 1800s, Dalton kind of viewed atoms as just like a billiard ball, just a ball that was indivisible and nothing that could happen to it. And a lot of times when we draw pictures of atoms, that's what we kind of draw. Over the course of the century, the parts of the atoms, like the electrons, were developed. So Thomson thought that there were these electrons all over the place and sort of embedded in this whole thing that was positively charged. And then in your book, they talk about Rutherford's gold foil experiment. And he discovered that the positive charge was mostly in the middle. So the vast majority of the atom is empty space, and the nucleus is very, very small. It's about 10,000 times smaller than the rest of the atom. So for comparison, if the atom were the size of a football stadium, the nucleus would be the size of a nickel. So it's really, really, really very small, but almost all of the mass is in that nickel in the middle of the football stadium. Because almost all of the mass of the atom comes from that central part there. There are some more developments, and what we're going to look at today is what was going on with the electrons. And so this is what's often called the Bohr model of the electron, and I'm going to open this up so we can kind of see the animations here. Hopefully that's popping up. Or maybe not. Got my lovely pinwheel going on here. Well, let's see. Guess I'll have to open that back up again. All right, so while I'm waiting for that to open again, have either of you done dot structures in chemistry before? This is kind of beyond what we're going to talk about today, but dot structures where you draw a molecule with the chemical symbols and have the dots in there. You can just open up your microphone and, let me know. Have you done those before?
I don't think so.
Okay.
I don't think so either. I know I've heard of them, but I don't think I've actually done them before.
Okay, so we're just going to get like a glimpse of how you start with those today, but that's in chapter 3, which is coming at the end of the week. So what I have done for one of the topics that was from this chapter, I'll continue to do for other topics, is that I will put sort of a mini lecture onto Canvas to kind of help guide you. But I'm going to try next Monday to spend some time talking about how to put together those dot structures, because I know that's something that sometimes people struggle with. All right, let's try. This. Okay, I'm going to try this again. There. Okay, you should be able to see the slide now. So Rutherford's idea was that the positive charge and the neutrons were in the middle. So I've got the blue with the plus signs in it are our protons, and the neutrons are kind of in there as well. And the electrons are somehow on the outside. But of course, this doesn't really make sense if we think about how opposites attract, because the negative charge should be attracted to the positive charge. So why didn't the electrons go and just crash into the middle? And so Bohr's model says that the reason that they're not crashing into the middle is that they're kind of like planets in a solar system, that they're moving around the nucleus. So just like the moon doesn't crash into the Earth because it's orbiting us, the electrons don't crash into the nucleus because they're just kind of going around in circles. And so we're going to use this idea of these circles, which we'll sometimes call shells or layers, to understand which electrons are going to be reacting and which ones are just going to kind of stay put. And so we're going to divide that up into the core electrons, which are on the inside, and the valence electrons, which are on the outside. So in this model here, I just want to point out that on the first inside ring, there's only 2 electrons, and we're going to see that's kind of the view that we take. And then on the outside, there's more, and we can get up to 8 electrons on the outside. And just kind of a quick note as to Bohr's model, what evidence does he have for this? And that came from the different colors that different elements would give off when you burned them. And so he said that we can tell the difference between these different layers by the colors that they give off. So if light goes in, it's going to bump an electron to a different layer. And then when that electron falls back down to the appropriate layer, it's going to give off that color. And so the color is associated with how far apart those layers are. And the mathematics of it and all of that work out really nicely so that we can tell the energy levels of the different layers. So there's a lot of evidence for this. Okay, so we've got most of our atoms kind of look like this, and I've shown the rings getting closer and closer together as they get farther apart because the energy levels do that each energy level layer that we add on is just a little bit higher than the one before it, except for the first ones are more far apart. But we don't want to have to draw an entire atom every time we're talking about our electrons or the energy levels. And so what we tend to do is we tend to use horizontal lines to show these. So our first layer, the inside layer here, the smallest circle, we're just going to show with a very short line. And then our next layer, oh, and I said that one can only hold 2 electrons. Then our next layer, we would show with a longer line. Now, usually we divide this up into 4 segments that each hold 2 electrons, but I'm just going to show it right now with 8 because those individual segments don't really matter to us right now. And then we can do that with each of our layers. So the first layer holds 2, and the next layer holds 8, and then beyond that they add more, but it gets a little complicated where they divide up, but there's always like 8 in the last segment of it. So we just kind of think about that 8. And the other electrons deal more with the transition metals, the metals that are like in the middle of the periodic table in that kind of lower down area. And we're not going to worry too much about those right now. We're just going to be focusing on the ones that do this thing in sets of 8. So that's what we're going to focus on. All right. And so then we have these other energy levels that are up there as well. All right. So in your book, towards the end of chapter 1, it talks about how we have S electrons and P electrons, and we can do these electron configurations. I do not need you to do electron configurations. You don't need to worry about S and P and all of that stuff. If you were to go on in chemistry, you could learn that, but it doesn't really become useful until you're taking organic or inorganic chemistry later on. So for our purposes, all we need to know is that we just have these layers, and the first one is 2, and after that it's 8. So what we're trying to get to is figuring out for any given element how many valence electrons we have. What are the core electrons? What are the valence electrons? And so we're going to follow this rule that says the electrons have to go to the lowest energy level that they can. So they can keep going down to the lowest energy level till it's full, and then they go to the next lowest energy level until it's full, and so on and so forth. So if I have a hydrogen, there's just one electron, it can go to the lowest energy level. And then if I have helium, there are 2 electrons, so second electron goes to the second energy level. But when I get to lithium, that first energy level is full, so that third electron is going to go to the next energy level. And so what we're going to start to see is that for the atom, the outside layer, and our outside layer here, you can see only has 1 electron. The outside layer is going to tell us how many electrons there are and where it shows up on the periodic table. So and I'll show you a periodic table in a second, but if you have one handy, you'll notice that right underneath hydrogen is lithium. So they both have just 1 electron in that outside layer. Now the next element is beryllium, and beryllium has 2. So you might wonder, well, why isn't beryllium right underneath helium? And this is because helium's layer is full, and so we have that in a special category called noble gases. But beryllium, it still has 2 electrons, but it's not full. So since it's not full, we're not going to put it right underneath helium. So we're going to kind of start a new column with beryllium. And we can keep adding these things until we get to first neon would have that full, but sodium has 11 electrons. So right now I'm showing 10 electrons. Once I add the 11th electron, it goes in the next layer. 1 electron in that outside layer, and so it's right underneath lithium on the periodic table. So hydrogen has 1 outside electron, lithium has 1 outside electron, sodium has 1 outside electron. And those outside electrons are called the valence electrons. So what happens for an atom is that only the outside atoms or outside electrons can react with other chemicals. The inside ones are just sort of stuck in place and they don't really do anything. But that outside one can do a couple of different things. It can be given up, or it can get lost, which often happens with our metals, or we can add to that layer. We can add extra electrons to that layer, or the electrons can be shared with other atoms. And so those are all the different ways that we can have chemical reactions. All right, so we have magnesium here. Magnesium has a second electron in that layer, and if we look on the periodic table, magnesium is right underneath beryllium. So beryllium had 2 valence electrons, magnesium has 2 valence electrons. And that's kind of how we build that periodic table. All right, so we talked about a couple of definitions here, and this is all directly from your book, so you don't need to jot this down right now if you don't want to. But the main ideas here are getting the difference between the valence electrons and the core electrons. So valence shell electrons are in the outermost layer. If I put a number with it, it's the highest layer. So we talked about the first layer, the second layer, the third layer. And that those are the ones that actually do the chemistry. So if I have a full valence shell, if I have all of my electrons in place, like I do with the noble gases, then there's not a lot of chemistry that's going to be going on, because atoms are going to try and react in order to fill out that valence shell. And the core electrons, again, are the inside ones. They don't really do anything, so we can kind of ignore them. All right, and again, just saying this again, that the elements of the same group or column, so group 1 has 1 valence electron, group 2 has 2 valence electrons, and then we're going to skip over that flat area in the middle of the periodic table and start counting on the tall columns again. The third column, starting with boron, has 3, the fourth one with carbon has 4, and so on. So you can just count the columns to see how many valence electrons there are. So what happens is these atoms, if you start with a neutral atom that has an equal number of electrons and protons, those neutral atoms are going to chemically react, and they're going to chemically react to gain electrons, lose electrons, or share electrons, all in the goal of getting a full valence shell. So if they're close to filling out the 8 electrons, they're going to try and either share electrons with another atom or gain electrons. But in the case of sodium or lithium, it's going to be really hard to get to get 7 electrons. It's a lot easier to just give up one, and then the layer underneath is full. So we have those different ways that they can react. So if I have very few valence electrons, and we typically call these metals, they tend to lose those electrons. If I have a lot of electrons, so I have 6 or 7, something like that, it's a lot easier to gain electrons. And then if I'm somewhere in the middle, if I have 4 or 5 electrons, then that's where I'm doing a lot more sharing than really trying to gain the electrons or lose the electrons. And so the sharing of electrons is in chapter 3. What we're going to focus on in chapter 2 is just the ions where we've lost electrons or the ions where we have gained electrons. So any questions at this point?
I'm good.
Excellent. Thank you for responding. That's really helpful for me. Okay, so I mentioned that we would start looking at dot structures. So in chapter 2, they start looking at, well, what do these dot structures look like for an atom? So what we do is we write the chemical symbol. So these symbols are just from the periodic table, and then we count the valence electrons and we put them, each dot represents one of those valence electrons, and we sort of imagine an invisible square around the chemical symbol. And we put a dot on each side of the square until we've filled up all 4 dots. So we spread them out as much as we can at first. So you notice that, like with beryllium, we don't put 2 dots together, or with boron or carbon, we don't put 2 dots together. We spread those dots out as much as we can. But once we've hit 4 sides of the invisible square, then we have to start pairing them. So with nitrogen, we pair them up. Oxygen, we pair them up, so on and so forth. And so electrons like to do things in pairs. And so what ends up happening, sorry for that sound, a bird just ran into my window. The places where we have only 1 electron, if we count those electrons for the ones that are kind of in the middle, that tells us how many bonds that element likes to make. So boron likes to bond to 3 things. Carbon likes to bond to 4 things. Nitrogen likes to bond to 3 things. So we're not looking at the total number of electrons, just the ones that are by themselves, the unpaired electrons. Those tell us how many bonds they'll make. I'm not going to dwell on that right now because we're going to be focusing on ions, not on sharing. So if we look at lithium and beryllium, they only have 1 or 2, and it's pretty easy for an atom to give up 1 or 2 electrons. And so those tend to form positive ions, what we call cations. And then on the other side, we have oxygen and fluorine that are really close to full. So it's a lot easier for them to just snag an electron from, say, a lithium or a beryllium that is ready to give it up and fill out their shell and become oxide, which is -2, or fluoride, which is -1. And then neon, it's already full. So it's like, I don't need you. I'm just going to hang out and do my own thing. All right, so your periodic table is kind of broken up into 3 areas, and it's really important to know where your element falls in these particular areas to know how it's going to react. So there's sort of this diagonal line, and on here it's orange, that is where the semi-metals are. And then to the right of those are our nonmetals. So all the nonmetals are on the right-hand side with the exception of hydrogen. And we're going to find hydrogen as an exception in a lot of places. We call it the problem child because it doesn't behave the way the other elements do. So hydrogen's hanging out over there with lithium, but it really acts like a nonmetal. So all of the other nonmetals are over on the right-hand side. Nonmetals tend to form negative charges, what we call anions. So if you think of anti as being negative, an anion is a negative charge. And they're going to be on the right-hand side, with the exception of the noble gases. Of course, the noble gases don't form charges at all. And then the vast majority of the periodic table you can see are metals. So it's the whole middle section, that chunk at the bottom are all metals. The left-hand side, with the exception of hydrogen, all of those are metals. And then even a little bit on the lower part of the right-hand side. The semi-metals are kind of unusual. These are elements that will have one or more, or that will have one form or possibly more than one form that behaves as a metal and one form that behaves as a non-metal. So these forms are called allotropes. So for example, carbon is sometimes graphite, which is what's in pencil lead and kind of leaves that dark gray residue. But carbon is also diamond. And both of those only have carbon in them, but they're very different. So those are different allotropes of carbon. So in the case of silicon, or in the case of antimony, we have one form of each of those elements that really behaves like a metal and one form that really behaves like a non-metal. So we're going to try and leave that section out of our discussions of ionic versus covalent bonding, because they can kind of go in different directions, and I'm not trying to confuse you. So what I really want you to focus on is the things we know are metals versus the things we know are non-metals. And in chapter 2, we're looking at ions. So we're going to look at the things that form these charges and then get together in an ionic bond. Whenever you have an ionic bond, you're going to have one thing that's a metal and one thing that's a non-metal. All right, so we had talked about how on the periodic table you can tell how many valence electrons you have based on the column. So there are a couple of different ways we number the columns. So sometimes you'll see it just goes across 1, 2, 3, 4, 5, 6, 7, 8, 12, all the way up to 18. And then sometimes you'll see it where they will have Roman numerals instead of regular numbers, but then they'll have like the letter A. So it'll be 1A, 2A, 3A, 4A, 5A, so on and so forth. And when we use those numbers, whatever the number of the column is tells us the number of valence electrons. But when we have a table that looks like this, you just have to remember that when we get to this third column here, we're ignoring the middle area, this third column where boron is, instead of 13, it's just 3. So for carbon, instead of 14, it's just 4. So you just drop that teen part of the number and leave it as 3, 4, 5. What I tend to do is I just start counting the elements, skipping over the middle. Oops, go back there. So if I were looking at phosphorus, I would say, okay, let me start at the beginning of this row. I have 1 for sodium, 2 for magnesium, 3 for aluminum, 4 for silicon. So phosphorus has 5 valence electrons. So if I were looking at, let's say, let's look at chlorine here. How many valence electrons does chlorine have?
7.
Exactly. So we can see that because it is in this column when we just drop that teen, or we can count from the side 1, 2, 3, 4, 5, 6, 7. So when we get into doing more dot structures in the next chapter, that's going to be really helpful. Now, if chlorine has 7 valence electrons and it wants 8, how many electrons is it likely to pick up?
I guess 1.
Yeah, just 1, exactly. So all of the elements that are in this column with chlorine, fluorine, chlorine, bromine, iodine, they're all on that same boat. They all have 7 electrons. They only want 1. And so we will see these almost always with a -1 charge. Similarly, if I'm looking at oxygen, sulfur, and selenium, and we're just going to stop when we get to this zigzag line. So we're not going to go down to polonium. We're just going to say oxygen, sulfur, selenium, tellurium. These will form a -2 charge. And then on the other side, if I have, we said hydrogen, lithium, sodium, all of these have just 1 electron. Well, they can only lose 1 electron from their outside layer. The inside layers don't do anything. So they tend to form a +1 charge. So group 1, really easy to remember. Group 1 forms +1. Group 2 forms +2. So those two and the columns over here, the -1 and -2 columns, are really good ones to just kind of remember. That entire column will be -1 for the fluorine, chlorine, bromine, iodine, and the entire column with oxygen will be -2. And that will kind of help you combine things very readily. So we have names for those columns. I think they go through those in chapter 1. But the first column we sometimes call the alkali metals. The second one, the alkaline earth metals. So metals are there in the name. That helps you remember they're metals. And then fluorine, chloramine, and bromine and iodine, those are our halogens. And halogens means they form salt. So gen, like Genesis, is to make something, and hal refers to salt. And so these will combine to form different salts. So sodium chloride is table salt, but anytime we start mixing negative and positive charges, ionic compounds, those are what chemists will call salts. So even if it's not sodium chloride, if it were lithium fluoride or potassium bromide, we would still call that a salt. And so that's why we call those halogens. All right. So one last thing that they mention in chapter 1 that isn't going to be real important until later on, but it is kind of an idea to have in the back of your head, is that the elements kind of do this weird thing as they go across the periodic table. So they've left out the transition metals here because the transition metals don't always behave like everything else, and it's just a lot easier to look at the other ones. We call these the main group elements. So as you would expect, the elements near the top are smaller and the ones near the bottom are bigger. That is completely normal. But if we go across the periodic table, lithium is element 3 and neon is element 10. So lithium has 3 protons, 3 electrons, 4 neutrons. And here it is bigger than neon, which has 10 protons, 10 electrons, and 10 neutrons. So this has a lot to do with that empty space that we talked about. When we have a big positive charge like we do with neon, then it's going to pull on those electrons a lot more and get them closer to the nucleus. And so the size gets smaller as we go across, and it's really pretty dramatic. So if we look at lithium here, which is fairly near the top, it's element 3, so it's one of our very, very first elements, and then compare that to iodine. Now iodine's near the bottom on the right-hand side. Lithium is bigger than iodine. Iodine is element 53, so a lot more mass, a lot more protons, a lot more neutrons, but lithium is bigger in size. And that has to do with the power of that nucleus to pull those electrons in. And that trend continues across each row because we're talking about the same layer of the electrons as we go across that row. But once we add a new layer, kind of like adding a new leaf on a cabbage or a leaf on a head of lettuce, now we're expanding outwards. And so it's going to get bigger as it goes to that next layer. And this is going to lead to a property called electronegativity. And so the main idea is that these little atoms, all of the small ones, like to attract electrons to themselves. So they form negative charges. That's what we said about the nonmetals. The ones that are really big, so whether they're on the left-hand side or they're on the bottom, they tend to not really keep track of those electrons very well. And so they give them up more easily. So we say they're less electronegative, or sometimes we say they're electropositive. It's more common just to say they're less electronegative. And so that idea of electronegativity is going to come back again in chapter 3. So I just want to kind of plant that seed for right now. All right, so we looked at the layers here. If we are trying to figure out the charge of something based on the number of protons and electrons, we can see that in a neutral atom, we have to have the same number because each proton has the same amount of positive charge that each electron has a negative charge. So I'm going to have 11 protons, 11 electrons, and it will be a neutral overall charge for the sodium here. But it likes to form an ion where it removes that one electron from the outside layer, and so we only have 10. And if we only have 10 electrons total, then we have the protons, 11, 10 electrons, and a +1 overall charge. So we can kind of, guess and check how does that all work out. but a really good way to think about that is just take the number of protons minus the number of electrons. So 11 minus 10 is going to give me a +1 charge. So if I look at this next example with chlorine, of course, on the left-hand side, we have its neutral. We have that one open spot there where it can fit in one more electron. If I put that electron in there, I now have 18 electrons. So 17 minus 18 gives me a -1 charge. So, so we can use protons minus electrons will give us the charge of something. And then you can kind of reverse that if you know what the charge of something is and you're trying to figure out how many electrons it has. You can say, okay, I know that, say, magnesium has a +2 charge, and I know that it is element 12, so it has 12 protons. So 12 minus what gives me +2? And you can just sort of rearrange that and say, oh, it's 10 electrons. So that's how you can figure out charge and number of electrons. I mentioned before that there are some columns that have pretty consistent charges on them. So group 1 is always +1, group 2 is always +2. Beryllium is a little bit weird, but we won't see it in anything that we do. The group 8 over here, the noble gases, they're blank, but they're always 0 because they don't react with anything. And then we have the negative charges, the -1 charge for our halogens and the -2 charge for our oxygen group. That's actually called the chalcogens, but people don't use that term very much, so I won't really focus on that. So this might be a good table to have in reference as you're going through assignments or going through your quizzes or tests, to just kind of have handy, okay, what's the charge that this particular column does. You can kind of refer back to this until you kind of get the hang of it. And you'll see that aluminum here is in this third column. So it kind of behaves with that same trend as the other things in its row. So sodium is +1, magnesium is +2. They left the plus off there, and aluminum is +3. So it kind of behaves in that same way. And the elements underneath it will also form +3, but they can do multiple ones. So the ones we've left blank here, sometimes they might form a +3 and sometimes a +1. So we don't know what it's always going to be. So this chart is the one that pretty much anytime you see this element, it's definitely going to be this charge. And then the ones that are in the same columns but are left blank, it depends on the situation. All right, and then this is kind of an expanded version of that, but what you can see is that in this middle area, what I call the transition metals, most of them have multiple charges that they can be. And almost all of them have a particular charge, with the exception of group 1b. You'll see almost all of these will form a +2 charge, and that nickel should also be +2, but it also forms +4. So I need to fix that table. I'll have to write to them and let them know about that. But this is one of the reasons why we kind of leave transition metals out of a lot of discussions of these things. But what that's going to mean is that when we name a compound, we can't just say, oh, it's titanium chloride or it's chromium oxide, because it has different charges. So we have to tell what that charge is when we're naming those compounds. So I'm just going to briefly talk about naming compounds here. There are a couple of different ways that you may have heard of doing this before. So if you've had a chemistry class, you might have talked about using names like for iron. So iron is this Fe here. That comes from the Latin name ferrous. So we would say ferrous chloride or ferric chloride. We change that ending in there. I'm not going to worry about those because that doesn't really, that's not really helpful if you're not familiar with what charges those things form. So we're going to use what's called the stock system. And so with that system, when we have an element that is in the middle, then we would put a Roman numeral after it. So if I have a titanium with a 2+ charge, when I'm naming something that has titanium in it, then I would say titanium, Roman numeral 2, and then whatever it's combined with. So if it were titanium TiCl2, then I would say titanium, Roman numeral 2, chloride. If it were titanium with a +4 charge, then I would say titanium, Roman numeral 4, chloride. Manganese, they've listed 2 of them, but it actually has about 5 different oxidation states it can use. So I could have manganese, so this is Mn in the middle, a little bit different from magnesium. The names are very similar, but manganese is right in the middle of the transition metals here under 7b. And so I could have manganese 2 oxide, manganese 4 oxide, manganese 3 oxide, manganese 7 oxide. And so we use the Roman numeral to tell us what the charge is on the metal for those transition metals. But we don't have to do that for the first 2 columns because calcium is always going to be 2. So rather than sticking a Roman numeral in there that everybody knows it's Roman numeral 2 anyway, we just leave that out. All right, so does that kind of make sense how I'm describing the difference between the transition metals in the middle versus the first 2 columns?
Yep, I'm good.
Yeah.
Okay, great. All right, so they just briefly touch in chapter 2 on the 2 different kinds of bonds. So the main thing I want you to get out of this is that when we have a bond that is a covalent bond, it's usually between nonmetals and they're sharing the electrons. And when we have an ionic bond, that's really between a positive charge and a negative charge. So we have the metals form the positive charge and the nonmetals form the negative charge. So we'll have a metal and a nonmetal. And the idea in both cases is to get them to those 8 electrons. So we call that the octet rule. That's what you see at the bottom there. So they want to get to 8 electrons in the valence shell. And again, hydrogen is our exception. It's our problem child that doesn't behave like the others. It never wants to have 8 because its shell only has room for 2. So in order to fill out that shell, it just needs 1 additional electron. So the octet rule for hydrogen is to get to 2 in the valence shell, but everything else is trying to get to 8. All right, so this slide is focusing on the ions. So just kind of key idea, when we say ion, we mean it has a charge, and the reason that it has a charge is that there are not equal numbers of protons and electrons. And when we have an ionic bond, we have something that is positive and something that is negative, so oppositely charged things. And an ionic compound is a compound formed when we get those positives and negatives together. When we form an ionic compound, we have to have what's called charge balance. We have to have an equal number of positives and negatives. So if I have a 2+ metal and I'm combining it with a -1 nonmetal, I can't have one of each because I'd have leftover positive charge. So let's say I have calcium. Calcium is +2, and chlorine, which is -1. I'd need 2 chlorines, 2 -1s, to equal the +2 in the calcium. So that's how we achieve charge balance. And so when we have even numbers, it tends to work out okay, but sometimes if we have what we call mutually prime numbers, and usually this means 2 and 3, so neither one of them is divisible by the other one, then what ends up happening is that, well, we can't just have one and say, oh, I'm going to add as many of the other until I get to it. Like we did with the calcium. We said we have +2, so I'm going to keep adding chlorines until I get to a -2. We can't do that with a +2 and a -3. So we have to do a little bit of a trick there. And okay, let me do the definition here and then I'll show you how to do this trick. So cation, remember, is the positive charge, and that's going to be our metals. And our anion is our negative charge, and that's going to be our nonmetals. Okay, I'm going to move over to the whiteboard to show you how to do combinations that are not real simple. So let me do, oops, the whiteboard. Okay, so let's say I'm trying to combine iron, which is 3+, and I can't really do superscripts on this very easily. and oxygen, which is 2 minus. So obviously -2 is less than +3, so I need more oxygen. So I might say, okay, well, what I'm going to do is I'm going to have a second oxygen. But now I've got a -4 charge, and so I have less iron. So now I need to add another iron. Now I've got a +6 over there, but I only have a -4 for my oxygen. So I'm going to add another oxygen. So this is what we would call guess and check. I just keep adding one side and the other until I have the same number. So now I have a total of, oops, +6 and -6. And so that's what we call charge balance. And the formula for this would be Fe, and we count how many there are. There are 2 irons, so Fe2O, and then we count how many oxygens, 3. So it'd be nice if we had a real systematic way of doing this. And the way that will normally work, the easiest way to do this is to just say, okay, I'm going to look at the charge on my metal, the positive charge, and I'm going to make that the number of the anion I have. So this is a 3+, so I'm going to use 3 oxygens. And then I'm going to have the charge on my oxygen and use that for my number of iron. So we can see the oxygen was a 2-, so we're going to use 2 irons. So, let me write this out again. We're going to use this number for the number of irons and use this number for the number of oxygens. And that's exactly how it worked out over here. So let me give another example. If I have vanadium tends to form a 5+ charge and oxygen, then what would be the formula? How would they combine? V what and O what? What do you think?
I guess it would be V2 and O5.
Exactly. So we're going to take the 2 from the charge of the oxygen. That's going to become the subscript here with the vanadium, the 5 from the vanadium, and that's going to be the subscript for the oxygen. And we're going to end up with V2O5. So that works really well if we have an odd number and an even number. The one place that it doesn't work real well is if we have 2 even numbers, and that might be something like Ti with a 4+ and O with a 2-. So if we did that, we might end up with Ti2O4. But we can reduce this, just like we would never say 2/4 as a fraction. We would reduce that to 1/2. We would say, oh, wait a minute, those are both even numbers. Let me simplify that and call that TiO2. Now in chemistry, the ones tend to be invisible. So if I have 1 of something, I just don't write that number. So it's really Ti1, but it's an invisible 1, O2. So does that make sense how we're combining those things?
Yes.
Okay, excellent. All right, I'm going to go back to the PowerPoint, which I'm almost done with. Here. And kind of move this out of the way so I can see what I'm doing. Oops. Why that's there. Okay. Okay, yeah, I think this actually is the last slide. Oops, let me go back to it. The last thing that I want to make sure that you see that is not specifically in the book is there are a couple of sets of molecules to know. So there's just one page called Molecules to Know, and it has 5 sets. The first set is the diatomic elements, and that means elements that when they're in their elemental form, there's nothing else there, they form in pairs. So this would be like oxygen is O2 and nitrogen is N2. So I'm going to go back to the periodic table for a second here. There are 7 elements that do that, and they form a 7 on the periodic table. So if I start with nitrogen, which is element 7, and I go over to fluorine and down, these are my diatomics. So I have N2, O2, F2, Cl2, Br2, I2, and then my problem child, hydrogen, H2. So those 7 elements form diatomics. And the reason that's important is a lot of times when you see a question on a quiz or a test, I might say, oh, and it reacts with oxygen, and you need to know that I mean O2. Or if I say it reacts with chlorine or hydrogen, you need to know that it's Cl2 and not just the atom. I'll never mean just the atom for those 7 elements. So make sure that you know those that are diatomics. And then the other set that's going to be important are the polyatomic ions. And that's where we have, instead of just one atom having a negative or a positive charge, it's a group of atoms. So when we have a nitrogen and 3 oxygens, we call that nitrate. When we have a phosphorus and 4 oxygens, we call it phosphate. Almost all of them are negative, except for ammonium. Ammonium has a +1 charge. So, and there's just a handful of them on each of them. So those shouldn't be too bad. And every time you take a quiz or a test, you're going to have access to your book. It's just really helpful to have that kind of mentally at the ready so that you can work quickly with those items. All right, so any questions over what might be on quizzes or tests that are coming up?
I think I'm okay.
Yeah, I don't
right.
have any at the moment.
If you think of something that you're having trouble with, you can shoot me an email. And then if it's something that's really difficult to explain, I'll try to put a little mini lecture on Canvas so that you can see. And let me stop sharing that and share, where is it? Chrome. On Canvas, if you want to see an example of what I did in this second module here, you have chapter 1, and then there's this little appendix here. Oh, and what I discovered was that some people, what I'm calling appendix 17 is actually showing up as chapter 1 for you. And so if that's happening for you, then chapter 1 is chapter 2. So you just have to look the next chapter. But if you click on this, it really is just going through compounds versus elements and mixtures. And I have a little mini, it's like 20 minutes here talking about the differences. So if that's something that you struggle with, you can watch that and that will hopefully explain it better. So if you have anything that you kind of need that little extra boost on, just shoot me an email and that will let me know that I need to add something on that. All right, well, good luck with you this week. The test will be available tomorrow starting at 10 a.m. And what I will probably do is have a link to a short article to read, a scientific study, and then ask you some questions about that. So it might be good if you're worried about time to read the article before you open the test. So you just kind of have an idea of, okay, what's going on in the article, so it's easier to answer those questions quickly rather than worrying about, oh no, do I have enough time to answer all of this? So you should see that tomorrow morning. If you don't want to work on it tomorrow, if you want to wait until Wednesday, that's fine. It just needs to be turned in by Wednesday evening. All right, have a good week.
Thanks, you too.
Bye-bye.
Thank you. Bye.